All right, so welcome back for chapter 10. In this chapter, we're going to take a look at the idea of correlation and then regression, specifically linear regression. But we're going to start in section 10.1, our first section, with the idea of what correlation is and how we can measure correlation or measure the strength of correlation. Okay. All right, so key concepts or key ideas that we're going to take a look at in this section are the introduction of the linear correlation coefficient, which we are going to use the lowercase letter r for. It's also sometimes called the Pearson correlation coefficient, named after one of the authors or one of the people who did some of the original work on this back when it was developed and, I guess, invented, if you will. Yeah. And so we're going to find that value, that linear correlation coefficient, which is a number that measures the strength or how well sample data fits a straight line pattern when graphed. Okay? So we're going to be using sample data, sample paired data. It's sometimes referred to as bivariate data, but think of it as a bunch of x's and y's, a bunch of data points where we have an x and a y. And then we're going to decide whether or not there is a linear correlation between those x's and y's. That is, could we model this with a line? Okay. Now, in this section, we're only going to be talking about linear relationships. So when we graph them, we're looking for something that will approximate a straight line pattern. There are techniques, there are ways to do non-linear relationships, but they're outside the scope of this course. We're not going to work on them here. Okay. And then the last thing we're going to do is we're going to talk about how that formal hypothesis test can be used to determine whether that linear correlation exists for population values between the two variables. Okay. So with terminology, correlation. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. Okay. When there exists a predictive relationship that by knowing one, we can predict reasonably the value of the other. Right? That's correlation in general. Specifically, when we tack on that modifier linear, as in a linear correlation, we are saying that what exists between the two variables, when there is that correlation, that we get a line. Now, a couple things here. Lines are straight, so calling it a straight line is redundant. I put that in there because sometimes people think that that's a line. That's not a line. The math definition says that lines are straight, and if it bends, it's a curve. So we're looking for a linear correlation, which means a line. Lines don't bend, lines are straight by definition. Okay? The linear correlation coefficient that we're looking for is going to measure the strength of that correlation, right? So basically what we're saying here is, if someone gave you a bunch of data and you plotted it, and it looked like one of these four pictures right here, we could measure the linear correlation coefficient R to determine whether it is a strong correlation or a weak correlation. Now, we also talk about correlation in whether it is positive or whether it is negative based on, does the overall pattern in the data increase as you move from left to right? And when it increases, like this one right here, we would say that if you were to put a line through it, that line would have a positive slope, or that we have a positive correlation. Okay. In the second one, upper right, if you put a line through it, that line would have a negative slope, so we would say that it has a negative correlation. All right. Now, if we take a look at those two graphs a little deeper, the one on the left, this one over here, the data is a little more spread out, and where it generally looks fairly linear, it's not really a perfect relationship, nor is it even close to a perfect relationship, but it's still a fairly strong positive correlation. Compare that with this one over here. Now, while of course it's negative, it's going down, but you see how much closer the dots, the points are to a line that we can put through them? Since they're closer to that linear pattern, we would say that one has even stronger linear correlation. Okay. The one over here on the left has a correlation of 0.859. one on the right has a negative correlation of 0.971. Basically, what we're looking for here is we're looking for a correlation as close as possible to either +1 or -1. Close to +1 is a good positive or a strong positive correlation, and closer to -1 is a strong negative correlation. Right? If you take a look at what's happening in this lower left-hand corner down here, this is garbage. There's nothing that I can say. No matter how I tried, there's no line of any slope that I could put through there that would do a reasonably good job of modeling that data. That's just garbage. Right? And it has a garbage correlation. Garbage correlations are correlations that are close to zero, either positively or negatively, like a small positive number, as it is in this case, or a small negative number would also be a garbage. It'd be no correlation, right? Be careful though, because sometimes we get caught. See how this guy, it looks like we could put a parabola through that really well. And it probably would model really nicely. It would probably correlate really nicely to a quadratic regression. But our job in this section isn't curves. Our job in this section is lines. And can you put a line through that? Well, no, I don't think I could. In any line I'd try to put through it, it isn't going to fit the overall pattern. So this one has a fairly poor correlation, 0.3, closer to 0 than it is to 1. And it's kind of obvious from the picture that we're looking at some sort of non-linear relationship, though, because it looks like I could find some sort of algebra that would fit that. It just wouldn't be a line. Right? All right, some properties of that. The value of that correlation coefficient, the value of that linear correlation coefficient is always between -1 and +1. It's always going to be somewhere on that interval. Right? We ideally want something closer to the -1 or to the +1 end of that scale with 0 in the middle. Out here, these are going to be strong negative correlations. A line's going to do a really good job of modeling that data. Out here, these are going to be strong positive correlations. A line's going to do a really good job of modeling that data. Negative correlations would just be lines with negative slopes. Positive correlations would be lines with positive slopes. In here, this is where we have that garbage data that doesn't map well to a line or maybe maps well to a nonlinear, but it isn't a line, right? The thing that we're worried about in this section, the thing we're worried about in this course is what happens in here. Because if I gave you a -0.9, that's going to be a strong negative and there's no worries about that. If I gave you a +0.9, again, strong positive. But that middle ground in the middle there, we're uncertain as to whether that's good or whether that's bad, and we just don't know. That's the part where we really need to hypothesis test this and determine whether the data says it's good enough to be good or it's bad enough to be bad. Right? Where there is evidence to support or evidence to reject our null hypothesis and all that business. Right? Some other properties really quickly of it. If all the values are either converted to a different scale, the value of ours doesn't change. Meaning that if I took all the values for the x's and multiplied them by 10, or if I took all the y's and divided them by 3, and then reran this test, I would get the exact same r value. Because converting to a different scale doesn't change the value of r. So if your data is all in the thousands and you think it would be better to put it all in the hundreds, you could divide everything by 10 and r wouldn't change. Right? The other thing that doesn't affect r, by your choice of x and y. Let's say you're given data and the data you're given is in a table, but neither of them are labeled as x and y. Well, if you call these guys x and you call these guys y, or if you call these guys y and those guys x, it doesn't matter. The value of r would be the same. So which you choose doesn't affect the value of that linear correlation coefficient. R measures the strength of the linear relationship. Okay? That's all it's good for. If your relationship is not linear, like this guy, don't use R to talk about it. Because that lowercase r, that linear correlation coefficient, by definition, only works for lines. Right? And then the last thing, R is incredibly sensitive, very, very sensitive to outliers. Right? And a single data point, a single point that is an outlier, can dramatically affect the overall in this. So when we're exploring this idea and we look at our data set, one of the things that was often done, one of the processes that is often done, is the data set is explored for outliers. And if there is an outlier, then we have to ask the question, why is this there? Was it an error? And if it's an error, it needs to get removed. If it wasn't an error, and we have to include it because it's actual data, we're worried about how much it could affect because it's incredibly sensitive to outliers. Right? The notation that we're going to be using in calculations, we're going to be talking about n's here, but n's in this sense stands for the number of pairs of data. How many XYs I have, how many pairs of data. Okay? We're still going to be doing all this summation stuff because we got sums of X's and sums of Y's. But since we have data that has X's and data that has Y's, all of this summation stuff might be the sum of X or the sum of Y or a sum of X squared or a sum of Y squared in this. Right? That R is going to be our linear correlation coefficient for our sample data. Its corresponding population statistic is rho. I know it looks like a P, but it's a Greek letter rho. Okay? Greek letter rho is the linear correlation coefficient for population data. Right? Remember the difference between populations and samples. We have data from a sample that we are using to do hypothesis testing for a population. Okay? The requirements for this methodology to work is that we have to have a sample, a collection of a sample of paired quantitative data, a bunch of X's and Y's. I can calculate R no matter how big or how small, but if I want it to be statistically accurate, statistically significant, and be able to make conclusions about that population data, I need my data to come from a simple random sample. Right? I need to take a look at the scatter plot first and confirm that we are actually looking for some straight line pattern. And I need to check to make sure I don't have any error outliers. Right? If I know they are outliers, they must be removed, but only if they are known to be errors. Okay? Now, actually, if you want to get way down in the weeds, these two right here are simplifications of the formal requirement that the pairs of the data must be bivariate, must have a bivariate normal distribution. But this, to test for this, boof, that is well outside the scope of what we're doing in here. Okay? So we are going to simplify and say, take a look at the graph, make sure it looks like it should be. You should be doing this. Make sure it looks like a scatter plot of a line or a reasonable line. And if there's outliers, check them. Okay? The math behind the scenes is this. The value for R is being calculated by this hot mess. Okay? Now, I remember not too terribly long ago when we used to do that by hand. We don't do that by hand. It would be, I mean, look at all that mess. That would be a tremendous amount of work to do that. And one error in any one of those silly summations, and the whole thing would be garbage. So we're going to let the calculator do the work for us because it's just a nice, easy, clean way to do it. Right? In general, we're going to round our linear correlation coefficient to 3 decimal places. Right? Why 3? Critical values and kind of a holdover from back in the day when we worry about that. But most of the homework is going to ask for that linear correlation to 3 decimal places, so just get in the habit of rounding it to 3. Okay? All right, So what is this going to look like in practice when we do our hypothesis testing? Well, our hypothesis testing is going to be about a population correlation coefficient, that rho again. Okay. And so we're going to set up a hypothesis test. So we need to calculate R, that sample correlation coefficient, and then we're going to determine whether or not there is enough evidence that the population correlation coefficient is significant. Meaning, even though R might have a high value or a low value, is it a strong enough with respect to the data? Is it strong enough to say that, yeah, there is a line that we should use to model this data? Right. So I'm going to go back up here, and I'm going to talk about it again. But I want to talk about with these visuals. Okay. Down here, this graph right here, this would most likely fail our hypothesis test. And what I mean by fail here is that our hypothesis test would show that there is no population correlation coefficient for correlation. There is no significant correlation, that putting a line through this would give us no predictive ability. These two, when we ran a hypothesis test on them, would most likely not fail. Okay? And we would argue that, yeah, there is reason, there is data, there is enough evidence to suggest that we should find the equation of that red line in the left one or that purple line in the right one, and that line could be useful in making predictions about the data. Like, for example, if you look at this graph on the left over here, and let me zoom in on it, it looks like we know data from about here to about here, meaning we know X values from about 1 to 10. And those X values from 1 to 10 are seemingly giving us Y values from about, what is that, about 5 to about 30? But what if X was 12? What would be the Y value associated with that? I don't have any data out here at 12. But if I knew the equation of that line, could I take that line out to 12 and find a prediction for Y when X was 12? That's my goal. I want to be able to do that. But before I do that, I want to make sure I should do that. And the should do that is when we run the hypothesis test on the correlation coefficient. Right? So let's scroll back down here. So let's take a look at what's happening. Right? So the hypothesis test that we're going to run will determine whether the sample correlation coefficient provides enough evidence to conclude that the population correlation coefficient is significant. This little bit right here, saying that the population correlation coefficient is significant, that's the part that if it is, if the data concludes that, then find the equation of that line and you can use that line as a predictor. Okay? The test we will conduct will be a two-tailed hypothesis test. Okay? The math behind the scenes, it's running a t-test. The reason it's running a t-test is we don't have population information. We don't have population means or population standard deviations. We just have sample information, sample data t-tests. Okay? If you needed to know, degrees of freedom for this test will always be n-2, where n is the number of pairs of data. That's just how this one works. Okay? You won't actually need to know that to run the test, but there might be a question that'll say, what were the degrees of freedom for this? It's always the number of pairs of data minus 2. Okay? All right, the steps: gather the data, input the data into the graphing calculator. Now, hidden, embedded in number 2 here is when we put the data in, we're going to that's a no. We're going to look at the graph and we're going to ask ourselves, should we be using a line? Does it look linear, right? So when I plot this stuff, am I getting something like this, where, oh yeah, I could probably fit a line through there? Or am I getting something like this, where I don't see anything going on, and I probably shouldn't be doing this? Okay? Either way, once we decide that we are going to do it, then we'll run the command linreg t-test, and then we'll take a look at the data with respect to the claim and the given level of significance. All right. Our first example, when we run this thing right here, our first example is this. Old Faithful, located in Yellowstone National Park, is one of the world's most famous geysers. If you've never seen it, it's pretty awesome. If you have seen it, I bet you think it's pretty awesome too. The duration in minutes of several of Old Faithful's eruptions and the time measured in minutes until the next eruption are shown in the following table. Use the technology tool calculator to calculate the correlation coefficient. The claim is that there is a correlation between the duration of the eruption and the length of time until the next eruption. At a significance level of 0.05, what can you conclude? Okay, so let's look at what's going on here. Our claim is that there is a significant correlation, right? So our claim is that there is a correlation. Okay? Now, luckily for us, when we do hypothesis testing on this, the hypotheses are always the same. The null hypothesis is always that rho is equal to 0. The alternate hypothesis is that rho is then not equal to 0. Remember, rho is our population correlation coefficient, right? So saying that rho is equal to 0 would say that there is no correlation. Saying that rho is not equal to 0, and what's hidden in that statement is that rho could be, whoops, not p, rho could be positive, meaning the line goes up, right? Or rho could be negative, meaning the line goes down. Okay? So saying rho is not equal to 0 is equivalent to saying that, yeah, there is some sort of a correlation, and it could be significant. So when we set these up, our hypotheses, I don't have to think about them. They're always the same. I just got to figure out which one goes with the claim. In this case, we are attempting to say that that is the claim. The claim is that there is a correlation. Correlation would be that rho is not 0. Okay? All right. I also have some data, right? My data. Well, my data is that table and an alpha level of 0.05, right? So now what I need to do is I need to get everything into the calculator so I can get it set up. So I'm going to pause the video, readjust the screen, bring the calculator up, and I'm going to put all of this data into my calculator. I'm going to put all of these into list 1, and I'm going to put all of these into list 2. Right? It'll be a moment for you, but it'll probably be 3 minutes for me. Okay, so I think it's closer to 5 minutes for me, but I got it all in. I took all of the data for the duration of the eruptions, put it in my list 1 over there on my calculator. All the, 3.2, 56. All the data from list 2 went into, from the interval between the next eruption went into list 2. And now I want to take a look at the graph. Now this is going to be a little tricky, so stay with me. I need to do a stat plot. Now the stat plot is above the y equals key. So I'm going to second function y equals to get stat plot. I'm going to go into plot number 1 there by just pressing it. I'm going to turn it on. It is going to be a scatter plot. That's the type. X's I'm going to put in L1. So I'm calling these guys over here my X and these guys over here my Y. And I'm going to mark it with a little dot. Okay. Now I need to adjust the window So it shows me x's that are like those guys and y's that are like those guys. It needs to set the scale properly. Now there's an easy way to do that, because I'm going to select zoom and I'm going to go down and scroll, because there's a zoom stat. And what that does is it automatically resizes the window to fit that plot that we just set up. So I'll press enter and I get this, right? Now I'm looking at that and I'm seeing a fairly linear kind of pattern to this. It's not perfect, but remember, it's not supposed to be perfect. It's just supposed to be reasonable. So I'm liking what I'm seeing. So I think we should continue with this hypothesis test. It looks pretty linear. Let's run the test. So stat, tests, linreg t-test. X's are in list 1, Y's are in list 2. My alternate hypothesis is going to be not equal to, and I'm going to scroll down. Don't worry about reg equation. I'm going to scroll down to calculate, press enter, and I'm going to look at what I'm seeing here. Now, the t there, okay, the t is 21. That's the standard test statistic. But I'm caring about my p-value. And so what's the p-value for this? Well, holy cow, look at that. 9.26 times 10 to the negative 16th. 9.26 times 10 to the negative 16th for a p-value. That means 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 9. That's my p-value. When I compare my p to my alpha, p is less than alpha. When p is less than alpha, we reject the null hypothesis. Okay. And since the claim was the alternate hypothesis, we would say there is sufficient or enough evidence to support the claim of a, and what was our claim again? Oh yeah, there's a correlation. A linear correlation. Linear population correlation. And that's what we're saying. Yeah, so that's what we're looking at here. I ran a hypothesis test. The hypothesis test told me that this data strongly suggests that a line's a good fit and that I should be able to use a line to make predictions. Now I want to go back and point out something in the data. Okay? So I'm going to go back to the graph and see how, like, kind of in this area right here, there's some missing data. If I knew the equation of the line that went through this thing, I could use that to make predictions for that missing region where I don't have data. Okay? Now, what is that missing data? Well, if you look over here in the actual data set, do you see how here we've got pretty solid data up to about 2.4? And then suddenly from there, we've got pretty solid data from 2.8, but we're missing like 2.4 to 2.8. That's that gap we're seeing right there. Right? Now there might be some small gaps elsewhere. It looks like there's a little bit of a gap here, right? But it's not as big. This is our biggest gap. And we could use a line to kind of fill that in. Right? Now, our job is not yet to find that line. Our job is just to determine whether we should find the line. Section 10.2 is actually about finding that line. Okay? All right, we're at 30 minutes, but we got a lot more to do. So I'm going to break this up into a second video, and we'll pick up here for the second one. All right, see you back here for part 2.